lens means different things to different people. To the serious photographer, it can mean the satisfaction of accomplishment. A picture is created which otherwise perhaps could not exist. To many other people who little realize it, a lens means good snapshots. Pictures like this that they'll always treasure. To those craftsmen who demand performance because photography is a profession, a lens means results. Day-to-day high quality in black and white or color. For no single item in photography at any level is better assurance of quality than the right lens on the right camera. Today we accept high standards of performance in a fine lens as a matter of course. But these high standards are possible only because of the care and skill that have gone into the manufacturing process. Where does a lens such as this begin? At Kodak, it begins in Hawkeye, one of the largest, most modern optical plants in the world, where development in all phases of optics goes on continuously. A request is made for a new lens, and it is turned over to the optical design department for investigation and action. The lens designer is always anxious to create a better product, and through the years, lenses have been constantly improved in speed, definition, and overall quality. But it's not an easy job to squeeze another stop out of today's already excellent formulas and work in the improvements too. As calculations are made, the working formulas must be expanded. Today at Kodak, this electronic calculator is used for this purpose. It mathematically traces the almost infinite number of patterns of the optical image. From the information it provides, the designer learns much of the behavior or performance to be expected of that lens. The calculator can do in several weeks what used to take as long as a year. The engineering department then has the responsibility of planning the manufacture, establishing the tolerances, showing in detail how the lens will evolve. 7 pieces of glass and 53 precision metal parts will grow together to form this fine lens. Lanthanum oxide, that's one of the principal ingredients used in making Kodak glass. The ingredients of this unusual glass, made without any sand, must be carefully weighed out, correct to 1 part in 10,000. Kodak glass, which is made principally from rare earths and boric acid, was developed several years ago, and its exceptional characteristics of high index of refraction and low dispersion make it practical to use it in only 1 or 2 elements of any lens. After the ingredients have been thoroughly mixed in the tumbler, the next step, charging the crucibles, takes place. 3 parts by volume of the dry chemicals melt down to 1 of the molten glass. The crucibles in the clay pots are made of platinum, and each one is worth many thousands of dollars. But it's not an extravagance. The platinum lasts indefinitely, and more important, since it does not oxidize at the high temperatures used here, the glass is completely free of impurities. The melt is now transferred to another type of furnace, in which the ingredients are stirred for several hours more. It doesn't show, but the various ingredients of this glass have different weights, and they settle, much like milk and cream in a bottle. The stir furnace mixes the glass thoroughly and reduces the temperature several hundred degrees so the mass is correct for pouring. And the pouring, though it appears simple, is really an exacting operation. The glass must flow at just the right rate so that it does not set up too quickly. The small prism is part of every melt too. It will be ground and polished so the index of refraction of this batch of glass can be accurately measured. And now the slab and prism are placed in this annealing furnace, where the temperature of the glass is gradually lowered for 24 hours so it may be handled. Somewhere in this spectrometer, that prism we saw earlier is being checked for index of refraction and for dispersion. As a matter of fact, samples of all glass used at Hawkeye are carefully checked before going into production. And now the various types of slabs and bars of glass are cut into cubes of the correct size and weight. Ordinary glass cutters are used here, but the skill that comes of long experience makes the difference. These sticks of hardwood come in hundreds of sizes, and used as they are here to guide the cutter, they make it possible to form accurate pieces of any size and weight. No, he didn't cut himself. The red on some of the glass is a clay dye for an identifying number. It will be burned out completely in the next step. And that step is molding. The pieces of glass must first be softened in these furnaces. That's clay dust he's putting in to prevent the glass from sticking to the bottom. When the glass is softened sufficiently, it is formed roughly like this, and then placed into the power mold that turns it into a lens blank. A lens blank has on each side an approximation of the curve that the final lens will have. The blanks are placed in iron trays or pans, and now undergo a very important treatment, fine annealing. They are placed in furnaces where the temperature is raised to 1160 degrees and is then lowered very gradually. So delicate are the controls for these furnaces that the temperature can be lowered 1 degree an hour. This gradual lowering of the temperature removes the strain from the glass, makes it less likely to have any stress pattern that could cause distortion. Annealing is used also to control the index of the glass. And so after 3 weeks, as in this case, the trays are removed and the blanks are nearly ready to begin the trip that will transform them into fine lenses. But first, an inspection, for there is a tremendous amount of painstaking work ahead, and the blanks have to be okay. The liquid in the bowls is called xylol. It's something like benzene. It has most nearly the same index of refraction as glass, and because of this, tiny defects in the blanks show up better. This is just one of many 100% inspections that take place during the manufacturing process. Now we're ready to get underway with grinding and polishing, and this is the first stage of that procedure. These heated iron shells are coated with pitch, and the blanks are placed so the curved side goes into the pitch. The almost flat part of the blank is up, and this is the side that will have the weak or shallow curve. The other side, with more of an arc, is called the strong side. As each shell is completed, it is placed in cool water to set the pitch. It looks like mud, but that's emery the man is scooping out and placing in the shell and on the spinning dome. This is used to grind the glass to the proper shape and thickness. Usually, 3 different grades of emery are used for each shell, 1 rough and 2 fine. The emery has a coarseness identification much like sandpaper, and the finest emery, of course, is used for the last grind. A brass gauge is used to check the curve. This simple method is quite satisfactory for the preliminary grinding. The blanks are removed from the block so the other side can be ground. This can be done the same way we have just seen, or on machines like this. The strength of the curve or the size of the lens makes the difference. Generally speaking, if less than 10 blanks can be spotted on a block because of the curve or the size of the lens, it is more economical to do them individually. And here's what does the job. This diamond-encrusted tool spinning at 11,000 revolutions per minute. The coolant keeps the glass from melting. Both thickness and curve are established here. Again, 100% inspection takes place. Next comes a step known as pitch buttoning. The lenses are placed in these metal forms, and then hot pitch is flowed into the openings. When the pitch cools, each lens has on its back a sort of button which is used in the next operation. In this next step, the lenses are moistened lightly with an adhesive and placed on this metal dome called a laying-on tool. This is transferred to a heated metal form, the exact opposite. The heat melts the pitch, and slight pressure is applied to be sure all the pitch makes contact. Then cool water sets the pitch, and the lenses are firmly in position. Now the weak side of the lens is ground and polished to completion. We'll see more details of this type of operation in just a few moments. That's a spirometer about to be used. It measures the curvature of a lens. And of course, in a shell like this, one lens is the same as every other one. After the first side has been polished, the lenses are removed and mounted on small blocks like this. Single spindles, they are called. Because of the strong arc of the curve on this, the second side, it is impossible to mount more than one lens on a block, and so these are polished individually. And this is a portion of the polishing area, a small section of almost a full acre where this precision work is carried on. And of course, the air in these rooms must be carefully washed and filtered to eliminate the danger of large dust particles which could scratch the lenses. There are as many as 5,000 lenses being polished here, and many take more than a full 8-hour day to be completed. For here, the everyday standard of measurement is in millionths of an inch. Completeness and evenness of polishing is checked by placing a test glass of the exact opposite curve in contact with a lens. When these surfaces meet, a pattern of light rings is formed, each less than a millionth of an inch deviation from perfect. Here's one with 6, so back it goes until it checks to 3 rings or less. And it's important to point out that these working test plates are checked themselves against masters used only for that purpose. This test must be perfect. No rings can show. Here in Kodak's test glass vault, perhaps the largest and most valuable collection of its kind, are stored thousands of master plates, at least one for every curve of each lens manufactured here. The next important step is called centering. This means that the edge of the lens must be ground smooth exactly at the same distance from the optical and physical center of the lens. In this plant, most lenses are centered on these automatic machines. Two highly polished steel cups are curved in such a way that when they come together and a lens is held between them, the only position the lens can take is the exact center. This is the only manual part of the procedure. From here on, we see the process without benefit of the water spray that cools the glass and washes away the grindings. The abrasive wheel grinds off the right amount of glass, puts a bevel on the proper edge, and more remarkably, repositions itself by means of electronic relays to compensate for the tiny amount of abrasive worn off during each complete cycle. But even so, this precision equipment is not taken for granted. When a new production lot of lenses is being centered, a sampling is made from the first few dozen, and these are checked on this instrument called a runout analyzer. Runout is the term used to describe the edge of the lens and its relation to the exact center. When the lens is placed between these steel cups and then rotated, the edge passes in front of a microscope. The eyepiece is calibrated in thousandths of an inch, so it is fairly easy to determine whether the lenses are within tolerances. Now, any lenses that form components are cemented together. They have been carefully cleaned and paired up. The lower half is placed in a metal fixture like this. A small amount of cement is applied, and with the other lens it is slowly and thoroughly worked out to the edges. The other half of the fixture holds the two lenses exactly on their optical centers. Low, even heat is used to set the cement. Next, all glass surfaces exposed to air are hard-coated or luminized. This increases transmission of light by reducing reflections within the lens. The lenses are cleaned and mounted in a rack like this. Then the rack is placed in one of these huge bell jars. Down inside, the girl has previously placed a pellet of magnesium fluoride. Under vacuum, this substance is turned into a vapor by a high electric current. The vapor forms a coating on the lens, which can range in color from amber to violet. And this color is carefully controlled, so the various elements that make up a lens are properly balanced for maximum purity of transmission in color photography. Here again, each lens is inspected on both sides to be sure the coating is even and the right color. We've talked so far only about the glass that makes a fine lens, but the metal mount is equally important. Any lens designer can tell you that. And first-class metalwork begins with proper tools. This jig bore does incredibly accurate work. Here it's boring a 1/4-inch hole that is held to a tolerance of a plus or minus 1/10,000th of an inch. One of the reasons for this amazing performance is the quill, as it is called, which is so steady that its variation from being true can hardly be measured. Preliminary work on automatic screw machines and lathes is maintained at high standards too, for the metal parts that hold and control the glass elements must be as accurate as possible. A sampling is made of the first few dozen, and they are inspected before the production run is made. Particular attention is paid to the threads, and these are most easily checked on this device called a contour projector. It magnifies the part 100 times in this case and shows readily the threads traveling past this chart, which is really an optical gauge. A part of the metal story frequently overlooked is the lettering on the mount, the name of the manufacturer, and more important, the data relating to distance and aperture. Here at Hawkeye, it is very carefully engraved by these machines that use a metal plate to guide the spinning tool. This method is accurate where it must be, and no part of the mount can be warped or twisted ever so slightly, as it could be if these letters and figures were stamped on. Well, then all the care that went into the making of the diaphragm and the diaphragm wings would be wasted. Here we see a large diaphragm assembly being completed and checked for smoothness of operation. Final assembly is another careful hand operation where the 9 major sub-assemblies are fitted together by expert hands. Where metal moves against metal, the parts are gently worked in with the appropriate lubricant. The future owner of this lens can be certain it will function smoothly and surely, that it will give him the superior performance he expects. And now that the major sub-assemblies have been completed, the lens itself takes form as a complete unit. Here once again, in an air-conditioned, dust-free area, the last elements are cleaned and locked in place, and the lenses receive a final visual and mechanical inspection. But that's only part of the story. Each lens must also pass a severe technical inspection in which the focus is checked and locked in and rechecked at all distances. And finally, a check on a lens bench to determine the quality of the image formed at the extremes of the angle of view. Checking and inspection of each lens has taken a lot of time, and equally important is inspection of the gauges used in production. Here, for instance, a Johansen block, itself a standard, is checked against a master on a sensitive air gauge calibrated in millionths of an inch. And even the master gauges are sent to the Bureau of Standards in Washington and checked every year. Wherever possible, fine equipment is used to verify gauges on the spot, and many special types of checks are made. There is no margin for error in a business that deals in these tolerances. This lens, which you have seen take form, represents the quality and performance built into all Kodak's fine lenses. Day in, day out, they can be counted on to deliver superior results. Whatever your interests are in photography, you can be sure that using a Kodak lens means best value. The name Ektar on a lens is your assurance that you are using the best. No finer lenses are made.